Hi, I'm Stacey and welcome back to my YouTube channel. In this video, we're going to be doing part 3 of my Zynq series. Part 1 was Vivado, part 2 was Vitis, and in this part 3, we're going to be adding our own logic to the Vivado block diagram. So we're back in Vivado today. This is where we left off last time, and I'm going to now be adding my own logic into this. So if we take a look at this image, you can see that this is what it's like before, which is basically just the block diagram. And Vivado has this wrapper file that it creates, and it is forwarding these internal signals out to the outside of the device. And this is what we currently have. And now today what I'm going to be doing is I'm going to be adding my own top level code because I want to add in my own logic to this. So this is my logic on this side. I want to add my own top level so that I can have both modules side by side. And the way that I'm going to interact with the block diagram is I'm going to have these internal signals that I'm creating that are signals that go from the block diagram to my code. And that's what I'm going to be using to interface with the block diagram. And we still have these signals that go out that are external signals. The purple ones are the ones that are leaving the FPGA and going to the outside world. And the red ones are the ones that I'm using to interface with the block diagram. And I'm going to be showing you how I put this together today. And the first thing I'm going to be doing today is creating these signals that go out of the block diagram to my code. So we can go here, and I can easily start by making the clock and reset. So typically you get the clock and reset from the fabric itself. But today, because I have a processor, like I mentioned in part 1, the processor is going to be supplying the fabric with a clock. So we are going to be using that clock, and that clock is currently in the block diagram. So I need to get that clock out the block diagram so that I can use it. And the way we do that is by clicking on the clock port itself. So now I'm clicking on the whole thing. I don't want the whole thing to be orange. I just want that part to be orange. So we click on the port itself, right click, create port, output clock. There we go. So now it's going to create this port out, which is this clock. I'm going to do the same with this peripheral reset, create port, output reset. There we go. So now I have my external peripheral reset and my external clock. And then the other thing I'm going to do is I'm going to create an extra block RAM port here so that I get to use a block RAM port and the PS gets to use a block RAM port. So this block RAM port is connected up to the PS. I'm going to modify this guy by double clicking on it. Now I want the whole thing to be orange and choosing dual port RAM, not dual port ROM, dual port RAM, true dual port RAM. There we go. So the one thing we must remember with this is that it's in 32-bit addressing mode. We can see that because if we go to the address summary, it's 32 bits. Even though the depth of it is only 2048. So the address mode is 32 bits. And what this means is that the addressing is for AXI addressing because it's connected to an AXI controller, which is byte addressing. So every byte on this RAM is going to have a different address. The bottom 2 bits are the byte address within the word. We must remember that because usually when you're working with block memory, the address is for the word itself, the entire word. Okay. There we go. So now we have the second port that's been created. I am going to make this port external. And now we've got our 3 ports. If I just regenerate layout, there we go. So now we've got my block diagram. So I am going to add some of the code that I pre-prepared beforehand by going plus and adding design sources. Okay, so here are my files that I've just added. So we've got my new top level file, my own logic BRAM file, and then now this is the point where we have a new wrapper. So that wrapper file was the top level file, and now I have a new top level file that I've made. So what I want to do is I want to quickly just right click and go create HDL wrapper, and I want Vivado to manage the wrapper. That's this wrapper, and update it. So I've added extra ports here, so I wanted to update those ports for me so that now my ports are also on the output of the wrapper. So if you look at the wrapper here, we can see that there's our BRAM ports, and there's our clock, and there's our reset. So if we look at this top level file, you can see that now I'm instantiating the wrapper, and I've split it up into internal ports here and external ports here. So these external ones are the ones that are going to get forwarded out on the top level, and these internal ones are the ones that I'm going to use to talk to my code, which is my Fibonacci sequence generator. So while this is building, I'm going to just hit go. First I need to move my face. Let me move my face. I'm going to hit build here. Yes, please. Thank you. Go. And while it's building, I'm going to give you a little tour of my code. Move my face back that way. Okay, so now that's going on in the background. So I have got my Fibonacci sequence generator that is interfacing to my block-RAM port, and that is going into the wrapper, into the block diagram. So if I open my Fibonacci code, we can see here it has a few things. The indentation is awful in this. Okay, so I'm going to go over, I'm using Emacs because I don't know why the indentation looks so weird there. It's got the same file open, but for some reason Vivado is displaying the indentation differently. So I'm just going to go through it using Emacs just because I like the way the indentation looks better. I can also do this, which makes it nice and big for everyone. So these are my BRAM ports, and these are the ports that interface to the block RAM. This is a fairly standard block RAM interface. The clock and the reset are self-explanatory, and then the enable port enables reading and writing. Actually, enable port enables it, and when it's enabled, then the data on the address will be written to the out. It's done already. Okay, thank you. And when the write enable is enabled, then the data in will be written into the memory at that address. So it's a fairly standard block RAM interface. So what this does is it has a Fibonacci sequence generator, and the Fibonacci sequence generator will generate a Fibonacci number every time get next number goes high. So when get next number goes high, a new sequence Fibonacci number will be generated, and that valid will go high for one data beat. So I have a counter going. Where's my counter? I have a counter going, and the counter just counts up to counter max. Every time the counter is 1, we get a new number. So the counter controls how often we write a new number into the memory, and in this case it's like every half a second we write a new Fibonacci number into the memory. The address keeps track of the address that the data must be written to, and it just increments every single time there's a valid. You'll see here that I shift the address left by 2, and that is because the address is the byte address, and I want to address the word, and the word is 4 bytes, so I have to shift by 2. I also have a write enable, which is 4 times the sequence valid, so it's 4 of the sequence valid in parallel. So this is fairly simple code. It basically just has a counter that counts up and keeps track of how often I get a new number, an address that keeps track of where that new number goes. We can look at the Fibonacci one itself. Zoom in a bit. When get next number is high, it calculates a new Fibonacci number in the sequence by adding the previous 2 numbers together, and then the most recent number gets shifted up into the next spot, and then sequence valid and the next number are just driven from that vector. And that's basically it. Now I've gone over the code and the build is done, so I'm going to export hardware. So the one thing that you must remember, I'm going to include bitstream as usual. One thing to remember is that this file changes. It was Zynq example wrapper, now it's Zynq example top, so it'll use the top level file name for this export. So when we change the top level file, we also change the name of the export. You can put in whatever you want here, but I usually leave the default, and if you leave the default, then this will change if the top file name changes. I'm gonna go yes, finish. So now we're exporting the hardware, and now we go to Vitis. So iterating on this is relatively simple. I did mention showing how I was going to iterate on this. You just re-export the hardware. If you have changed anything in Vivado, you re-export the hardware, and then we open Vitis. Here is Vitis. I'm going to move my face to the other side just because it makes more sense like that. So this is Vitis from last time. First thing I'm going to do is check that it works. I generally do this. I generally always check that it works without changing anything. I need to make sure that I'm picking the right one, and I need to update the file. So I'm going to right click and go update hardware specification. So we must remember to choose the right file. We have Zynq example top now. So we need to choose Zynq example top, because you'll see here there's two of them. There's Zynq example ramper and Zynq example top here. So we need to choose that one. Otherwise, our changes won't propagate. Okay. So when we choose Zynq example top, it's going to rebuild the entire stack. So this build process is going to take a while. And you can, well, not that long. Longer than usual. It's not like an extremely long process. It says it's been updated. You can see it says out of date here. So when it says out of date, if you try and go build here, it's going to rebuild the platform, and that takes a while. There we go. It's rebuilding the platform, and then it's going to rebuild the ELF file, which is my application code, and then it redid my ELF. There we go. So now I can go run. I need to open Putty though. Putty. There's my Putty. I'm going to open the Zebo board. Okay, there we go. And now we're going to run debugger. Oh, the board's not on. I'm like, why isn't it working? I'm getting errors. It's like Putty's erroring on me. Like, why is it working? Sorry, Putty. There we go. The board wasn't on. Now it's on. So we can check that it's working from last time. We can turn these switches off, and they go off. And it's working. So this is my code that I put in last time. Now what I want to do is I want to put in the loop a check for my memory. So I have that, and I also need int out data. There we go. So now this is reading the block RAM from the FPGA, and I'm going to do that every single second, because it's every 1 second. So what we're expecting to see here is every second, because my Fibonacci updates twice a second, every half a second, I'm expecting to see 2 new Fibonacci numbers every time I reload, every second. That is the plan. So I'm just going to build and run. Programming. Okay, so now it is, let me just make this longer. There we go. So I made it so that you can see more registers. So you can see we get 2 registers every single time, this every second. What you can see here is that once you start getting high enough Fibonacci numbers, the value overflows. So the Fibonacci numbers get beyond 32 bits. This is only a 32-bit register, and so we start seeing overflows. And because this is signed, it's going to end up having, the signs are going to come out weird as well. So that is why that's happening. Obviously, you can make this faster. I like to make it a bit slower because we can see it actively writing into the memory. If you have it too fast, then the numbers just appear. What I did also do, which is quite a fun exercise, is I just made it write all of the numbers into the RAM as fast as possible every second. And then you can like try and empty the RAM. You can like try and clear the RAM from the PA side, and the FPGA will just keep on putting numbers in there, and you can see like how much of it can you see as empty before the FPGA updates it again. So you can like have a war between the PS and the PL, where it's like the PL is writing into the RAM as fast as possible and the PS is deleting the stuff as fast as possible. You can like see who's winning. It's funny. So Obviously you can do more useful stuff with this, but I thought this was, well, you can do more useful stuff where you actually use the numbers on the PS instead of like messing around with them. Let me move my face back. So, but that's just me being silly. So you can do more useful stuff with this. You know, the PS can plot it and predict graphs or whatever you want to do. So it's quite nice. And that's how you do this. This is actually a bit of an inefficient way of doing this. A better way would be using an AXI interface. Doing it through the block RAM like this is possible, as I've obviously demonstrated, but slow. So if you want a faster version that is better, then the AXI interface is the way to go. And I think I may do that next. I think I'm going to write, because when I did my AXI video, I did a AXI master. So this would make a nice AXI slave. And it will be an example of how you can do something like this between the PS and PL a bit faster. That's that. So thank you for watching my video. I appreciate you. And I'll see you next time. And let me know in the comments what you want me to do next with this. I'll see you next time. Bye.